In this video we're going to go through some of the slides from Chapter 4. You should have read Chapter 4 prior to this. So we're not going to hit every single detail, but we'll hit the important ones. One of the very first things we do when we get a data set is to look at statistical summaries of the data. And the common metrics that are used include the average, the median, min, max, standard deviation, counts, and percentages. These are the standard measures. If we look at an example of the Boston housing data set, we can see that we have the mean here, min, max, standard deviation, median. We also get quartiles, interquartile range, and then for the categorical variables, the number of categories we have. So Charles River has a 0 and a 1. That's 2 categories. You might think of this as kind of a quick snapshot or big picture view of the data set. There are, of course, other things you can look at, graphs and tables and charts and things like that as well. But this is kind of where we start generally. To get this summary, go to the Boston housing data set, go to columns, column viewer, make that a little bit bigger. So select all the variables that you want to see the summaries for, and if you want to see everything that's in that table on the slideshow, then click Show Quartiles and then Show Summary, and here you get everything that is given here. Another way to quickly view the data in JMP is to use the Tabulate menu command, and to get there you go to Analyze and then Tabulate. And this is a drag and drop. You can pick different variables here that you want to look at and different summaries. For example, we could quickly tabulate the median value and do that by the Charles River indicator, so 0, 1, and we can look at the mean and the count. To do that, we're going to come over here. We're going to take the median value and bring that up here, and then we're going to take the Charles River and put that in here, and we want the mean there, and we want n also there, and actually we want those both there, so we'll highlight both of those and drop them in. If we want them in the same order, just drag the mean over there. So we have 22.09 for the 0 Charles River indicator. For the median value, 28.44, there's 471 and 35. And we can do something very similar where we have the categorical median value is either being low or high, and we can look at the mean value for the other continuous variables based on the categorical mean value, and then also the Charles River. So we can do this by first of all selecting the categorical median, drag that over here, drop it, and then everything down to LSTAT except for Charles River. If you try to put a categorical variable in here, it's going to give you problems. So drag this over here, drop it in, and notice it tells us for all of these things it gives us the sum. We actually want the mean, so we're going to drag the mean in over here instead. And finally, we do want the Charles River indicator variable, so we're just going to drag that down here. And you can see that we have exactly the same thing as what's given in this chart. So this allows us to look at these different variables: crime, zoning, index, NOx, and so forth, the average value for those in the low categorical median range and those in the high. So it looks like crime is on average higher, the lower priced houses, neighborhoods, and so forth. We looked at the correlation matrix last week, and this is another good measure for us to be able to quickly see what's going on. And in JMP it's nice because it color codes things according to size, and we would look at this and see, are there any correlations that are really high? If there are any around 90% or bigger, either in the positive or the negative direction, those would be ones that we would look at first to to drop one of the pair out of the data because of redundant information being contained in both of those variables. Now that's something that you would typically want to do if you were trying to fit a model and explain the components of the model, and we're not really so concerned with that in data mining because at the end of the day all we really care about is making predictions. So if there is multicollinearity, then that's not necessarily going to be a problem. However, we do want to be sensitive about how complex our models are, because the more complex they are, the more we tend to fit noise instead of the signal that's in the data. As you can see, this correlation matrix is actually rather large given the number of variables that we have, and that is really the source of the problem that we run into when it comes to having large data sets, is the number of interactions between two variables. We see that in the correlation matrix, but there are also other higher moment interactions, skewness, co-skewness, and so forth. So we'd like to be able to reduce the complexity of our data set. Reducing categories is a good way to simplify a data set. If you have categorical variables, for example, with m categories, you're going to need to transform that into m-1 dummy variables, which are going to either be 0 or 1 for the given category, and then that's going to make things even more messy because you're going to have lots of extra variables. So that can add up and make things unwieldy and make your computer run slow. So one way to deal with that is to combine categories, and sometimes you can see, even if it's not a categorical variable, zoning for example, we've got 90, 95, and 100 that all have 100% in the categorical median high class. And so we could combine those three together, and we've got several others that are likewise similar. 1, 2, 3, 4, 5, 6, 7, 8, 9. Those 9 variables are all very similar in that they all have 100% in the low categorical median value. So combine those things together, reduce the number of categories, and that's going to make life much easier to deal with. But the real reason we're doing this chapter is to talk about principal component analysis, and the idea here is that we want to reduce the number of numerical variables, and we do this by identifying where information is overlapping between the many variables that we have. Turns out that typically a small number of variables is going to contain most of the information, and so if we can identify those variables, then we can basically throw out the rest. And this is done by making linear combinations of the original variables, and these are just weighted averages, and linear combinations turn out to be highly correlated with the variable that we're trying to predict, but turns out they are uncorrelated with each other. So with, the dependent variable has a high correlation with linear combinations, but linear combinations are uncorrelated with each other. And so the new variables are what we call principal components. So with this breakfast cereal example, we have a bunch of variables, 13 it looks like or so, and here's a description of all the variables. So if we just look at 2 of them to start with, calories and ratings, and we look at the covariance matrix between these 2 variables, we see that calories has 379.63 as the variance, and ratings is 197.32. So if we add those together, we get 576.95, and 66% of that is explained by calories, 34% is explained by ratings. So the idea here is to make Z1 and Z2, which are just linear combinations of the original data, and it turns out they're going to have the same total variance as the original data points, but they're not going to have any correlation between them. So when we look at the principal components, we have what are called eigenvalues and eigenvectors. And if we look at the eigenvectors or the eigenvalues, that will tell us the proportion of the variance that is explained by each of these two different linear combinations. The eigenvectors, on the other hand, tell us the linear combination, or rather the weights that go on each of the original variables. So if we want to come up with the principal components, then what we need to do is take the calories variable and subtract its mean, and then multiply that by this score 0.847. Take the rating variable, subtract its mean, and multiply that by negative 0.532. Add those together and we're going to get negative 44.92. So this is the first principal component score for 100% bran. Now if you look at this formula, you'll see what I just described is not what's written down here. Turns out this extra negative 67.85 is the subtraction, is the part that comes from taking calories minus its mean multiplied by the coefficient plus the residual from rating minus its mean to come up with that. So don't worry too much about that number. The idea here is that we're taking 0.84 times the rating times calories, negative 0.52 times the rating, and basically adding those together plus a constant term. So when we look at Z1 and Z2, these principal component scores, we have correlation of 0 between these things. So in other words, there's no information overlap. So all the information is contained in Z1 and Z2. And we say, what's the variance of Z1? Turns out to be 498.02. We actually saw that already back here. 498.02. And the variance for the second principal component is 79.93. Turns out if you add these things together, you still get the same value of 576.95. So the variance does not change, but there's no covariance. So that makes us be able to say, well, the first principal component has most of the variance, so probably we can get away with just using the first principal component. Now, this makes the model less complex, but for large data sets, it's not necessarily straightforward or easy to calculate these things because you still have to go through and transform variables and so forth. But the model is less complicated. We can generalize this to having more than two variables. Say we have p variables, that means we're going to have up to p weighted average or principal components. All of these things are going to have a zero correlation. And so we're going to order these by variance, largest to smallest, and it turns out usually the first few are going to have most of the variance, and so the rest can be dropped. When we talk about variance, usually what we mean is information. So if we look at the principal components on this full set of data, we see that the first two have 55% and almost 38%. So add those together, give the cumulative of 92.86%. And we can come down here and actually look at the weights. So these are the coefficients. And we see principal component number 1 is heavily dominated by sodium. So sodium has a weight of 0.98. There's nothing even close in these other weights. Principal component number 2 is dominated by potassium, 0.98. Principal component number 3, calories, vitamins, and ratings to a lesser extent. So you can look at these eigenvectors or the coefficients, and sometimes it tells a story. And sometimes that story is easy to see and good story, and sometimes there's a problem with this. And the problem shows up in this case at least, in that sodium turns out to be measured in milligrams, whereas everything else in the data is measured in grams. So the scale for sodium is actually what's driving this, instead of sodium containing all the information. So how do we deal with that? Well, the simple answer is to normalize the data. Before we do that, however, let me show you in JMP how to come up with this output. And so to do that, you need to open up the serials data set, go over to Analyze, Multivariate Methods, and then Principal Components, and select Calories all the way down to Rating. Put that in here as Y columns, say OK. And what's going on here is that the principal components are actually being done on the covariances. So make sure you select that. And then if I click here and click on eigenvectors and eigenvalues, if I can move this up here. Looks like I can't. So we'll look at the eigenvalues first. We see here the first one is 55%, second one has 37%. Add those together and we get almost 93%. Look at the eigenvectors, which this is, you see sodium at 98%, and principal component number 1, potassium 98%, principal component number 2, and so those are the major drivers. So there's a story here that says sodium's driving this first principal component, potassium's driving the second principal component. But as we just mentioned, these things are on different scales. So if we normalize the data, what we're doing is we're putting them all on the same scale. And this is going to change the story. Sometimes it changes it dramatically, sometimes it changes it not so dramatically. But basically when we say normalization, we mean standardization, and that means subtract the mean, divide by the standard deviation. And so we can do that over here by simply saying, let's run this on, instead of on the covariances, let's do it on the correlations. And so you can see here that we have a very different picture. The first 4 principal components contain 74%. To get to 93%, we'd have to use the first 7 principal components, and that's not necessarily a bad thing. 7 variables is a lot less than 13, so our model is not nearly as complex, but we probably could get away with using just 4. But we can come down here then and look and see sodium now has a weight of 0.2 instead of 0.98, so it's not nearly as influential in the first principal component as some of these other things. So it turns out to be a story better told by calories, protein, fiber, potassium, and rating. Those seem to be the ones that are really dominating. Principal component number 2 is more about weight, whatever that variable is, potassium, sugar, and fat, and calories, it looks like. And so we would have to just decide where we would want to cut this thing and use a more simple model space or variable space in order to do our analysis. So how would we do this in classification or prediction and data mining? Well, we would apply principal components analysis to our training data set, decide how many principal components to use, and then use those weights to adjust any new data or validation data, and that would then reduce the number of predictor variables that we would use in our model going forward. Principal components is just one of the many ways in which to reduce dimensionality. Regression models or logistic regression is another way to do that. Subset selection, we'll talk a little bit about that when we get into those other models, regression and so forth. There are lots of other algorithms that are used to choose subsets of variables, and this actually is a very kind of hot topic right now in scientific computing. How do you decide which variables to use? Because models get very large very quickly. If you have 100 potential variables, then there are 2 to the 100 possible models, and 2 to the 100 is an extremely large number. In fact, that's on the order of about 10 to the 30, so one with 30 zeros behind it. So in summary, data summarization is very important in terms of being able to view what's going on with your data and decide what type of data mining techniques that you might possibly want to use. In fact, not only is it useful, but being able to reduce the complexity of the data is actually going to turn out to be essential for us. There are some computer programs that are limited in terms of how much data will even be allowed to be used, but believe me when I tell you there are data sets out there that are so big that they would crash your computer just trying to load the whole data set in. And so being able to reduce the complexity and ferret out the useful information is very useful. So that's what we've got for chapter 4, and we'll see you in the next video.